This is your presenter Asloob Mudassar, and I am presenting slide number 64 of the course on laser physics. Question is, discuss energy levels in a diatomic molecule. Also correlate the magnitudes of energies stored in different forms in a diatomic molecule. Answer. A diatomic molecule is the simplest molecule where the total energy of the molecule is contained in the electronic, vibrational and rotational levels. The electronic energy represented by EE is due to the motion of electrons about the nucleus. The vibrational energy EV is due to the vibrational motion of the nucleus, and the rotational energy ER is due to the rotational motion of the molecule. The translational energy is not quantized and will not be considered further. Electronic, vibrational and rotational energies of a molecule are all quantized. To compute the order of magnitude of energy difference between the electronic levels delta EE, we assume that the size of the molecule is of the order of A. That is, uncertainty in position is delta X is of the order of A. That is, an electron can be found in a molecule in this dimension. The uncertainty in the momentum is given by uncertainty principle as delta P is of the order of h bar over delta x. So substituting the value of delta x equal to A, we have delta P of the order of h bar over A. Thus delta EE is found from, so delta EE is equivalent to the delta P square over M. That is, the maximum amount of kinetic energy attained will be stored as the electronic energy. So delta EE is approximately equal to delta P square over M, and substituting the value of delta P, which is of the order of h bar over A, we obtain h bar square over M A square is the difference in the electronic energy, and this is shown in equation number 64.1. The potential energy stored in a diatomic molecule with atoms separated by a distance equal to r is given by U is equal to half K naught multiplied by the square of r minus r naught, where K naught is the spring-like constant and r naught is the equilibrium distance between the two atoms in the absence of potential energy. So you see that here R is actually the separation between the two atoms in a molecule. So if you set R is equal to R naught, then the potential energy becomes equal to 0. It means that the potential energy is minimum or equal to 0 at the position R naught. So R naught is the equilibrium distance between the two atoms. And the potential energy will increase if R is increased on either side of R naught. That is, R is increasing to the left or decreasing to the left. In both cases, the potential energy will increase because it depends upon the square of the distance, square of this distance between R minus R naught. The actual potential energy curve U prime of R differs from the parabolic energy curve U of the equation 64.2. So you see that the curve given the curve of U, if you plot the curve of U given by equation number 64.2, you will obtain a parabolic curve. But the actual curve represented by U prime of R is shown in figure 1. The figure shows the electronic state 1, that is the ground state of a diatomic molecule, which also indicates the vibrational levels. The derivative of the potential energy given by equation 64.2, that is the derivative of this equation with respect to R, gives the force exerted by the atoms on each other. The force is attractive at large separations, and then it becomes repulsive for small separations. That is, if R is, that is over here, if R is larger than the separation of R naught, then you see that the force will be attractive, and if R, this capital R, is smaller than the magnitude of R naught, then the force will be repulsive. So the force is attractive at large separations, that is larger than R naught. Then it becomes then the force is attractive at large separations, and it becomes repulsive for smaller separations, that is smaller than R naught. The force is 0 at R naught, at R is equal to R naught, which is the separation that the atoms tend to assume in the absence of vibration. So if you set R is equal to R naught, the potential energy is 0, and thus the force between the two atoms will be equal to 0. So this is the plot of the potential energy curve and the vibrational levels of a diatomic molecule. So you see that here we are plotting U prime of R as the potential energy as a function of R, where R is the separation between two atoms along the horizontal axis, along the vertical axis, and we are plotting the distance R, which is the nuclear separation. That is the separation between the two nuclei of the atom is plotted on the horizontal axis. The equilibrium distance R naught is also shown. So here 1 stands for the ground state, ground electronic state. So the ground electronic state is 1. And you see that if R naught is much larger than, that is if R is much larger than R naught, you will not see any vibrational levels, because you are then under the ground state of the atom. And under that condition, only the two atoms will behave as if they are independent of each other. And they have, the individual atoms have the electronic ground state, electronic levels, as if the molecule will have the electronic levels as if the individual atoms will have. So you see that when the atoms are in the vicinity of the distance R naught, of the separation R naught, then you can observe the vibrational levels. So if you move away from R naught, you see that the vibrational levels will increase, that is from nu double prime to V double prime to 0, it will increase to 1, 2, 3, 4 depending upon the separation of R. So if R is away from R naught, you will see that the more vibrational levels will be occupied. And similarly, if R is less than R naught, then you see that again the same levels will also be occupied. But you know that if you further decrease the value of R on the left hand side of this curve, that is on the left hand side of a parabola, then you see that the forces will be extreme, that the forces will be repulsive, and the strong nuclear forces will repel each other, that will repel the atoms. So R naught is the equilibrium distance, and if R varies around R naught, then you see that the separation will go on the right hand side, then the atoms will compress, and their separation will decrease below the distance R naught. So due to the vibrations, the atom will be on a distance R greater than R naught, and at the same time it will also be on, and after some time it will be on the left hand side of the distance R naught, that is it will be at a distance R less than the distance R naught. So in this way the atoms attached through a spring like forces will have a distance R greater than sometimes R naught, and similarly when the spring will compress, it will be shorter than R naught. So you see that in both cases the atom will tend to come to the equilibrium state R naught. But if it vibrates, then you see that it can occupy the vibrational levels shown over here with the label 0, 1, 2, 3, 4 and so on. So higher levels are also possible up to the ground electronic state. So let's read the text. If the atomic separation is large, there will be no vibrational levels. That is, if you are over here in this region, that is under the ground state, electronic ground state, then you see that there will be no vibrational levels. For the vibrational levels, R should be around R naught. So if the atomic separation is large, there will be no vibrational levels, and the electronic levels would be the same as those of a single atom. If the separation is finite, there will be interactions between the atoms. The electronic levels are modified and vibrational levels are created. as shown. Around the value of R naught, we have the vibrational levels in the form of a parabolic curve. If the diatomic molecule is at any distance R not equal to R naught, but in its vicinity, the internuclear force will cause the atoms to oscillate around the equilibrium position R naught, and the molecule will possess vibrational energy as well. Let's assume that the two atoms are displaced from the equilibrium position by an amount equal to the size of the molecule of the order of A. The potential energy stored in the molecule will be equal to the change in the electronic energy, delta EE. That is, the potential energy U will be equal to half times K naught into A square, and this will be equal to delta EE. But you see that for this we require that the separation between the two atoms in a molecule should be of the order of the size of the molecule, that is equal to A. So this is the potential energy, and this potential energy will be equal to the difference in electronic energy. Using A from equation number 64.1, that is from this equation, if you take the value of A from here and substitute the value of that A over in this equation and solve this equation for the value of K naught, you will obtain the value of K naught equal to K naught is equal to 2m delta E square over H bar square, as shown in equation number 4. The change in vibrational energy between two consecutive vibrational levels is given by the well-known harmonic oscillator expression. So the change in vibrational energy between two consecutive levels is equal to H nu naught is equal to H bar multiplied by square root of K naught over mu, where mu is the reduced mass given by mu is equal to m1 into m2 divided by m1 plus m2, and m1 and m2 are the masses of the two atoms. Using a K naught from equation number 64.4, that is from this equation. So if we take the K naught from that equation, the equation number 64.5, that is this equation, for the case of a mononuclear diatomic molecule reduces to, that is a molecule having the two atoms which are identical. For that atom we can write the difference in the vibrational energy between two consecutive levels is delta E nu, delta EV. V is the vibration, so delta EV is equal to 2 times the square root of small m over capital M multiplied by delta EE, where m is the mass of the electron and capital M is the mass of an atom. For a mononuclear diatomic molecule, the rotational energy in the jth level is given by, so ER, that is the rotational energy, is equal to H bar square over capital M into A square, and in the numerator we are multiplying with J into J plus 1 as shown in equation number 7. Let us compute the difference of rotational energy delta ER when the transition occurs between the jth and the J minus 1th level. So delta ER is equal to 2 times J over capital M multiplied by H bar square over A square. So this is the difference in the two consecutive rotational levels of the molecule. Replacing H bar square over A square from equation number 64.1, that is from this equation, if you take the value of H bar square over A square from equation number 64.1 and substitute in equation over here, that is delta ER is equal to 2J over M multiplied by H bar square over A square. If you replace H bar square over A square using equation number 1, you will get delta ER, that is the change in the rotational energy between two consecutive levels, is equal to 2J over capital M multiplied by M times delta EE, and that is equal to, that can be written equal to 2J multiplied by the square root of M over capital M, and then multiplied by the square root of M over capital M, and then outside that one we have delta EE. replacing the terms in the parentheses from equation number 64.6, we obtain delta ER is equal to J times m over square root of m over capital M multiplied by delta E nu, as shown in equation number 8. So if we choose m over capital M of the order of 10 to the power minus 4, it follows from equation number 64.6, that is from this equation, we get that delta, that the change in change in vibrational energy between two consecutive levels is of the order of 10 to the power minus 2 times the change in electronic state between two consecutive levels. And we also obtain that delta ER, that is the change in the rotational energy between the two consecutive levels, is of the order of 10 to the power minus 2 times delta EV, that is a change in two consecutive vibrational energy levels. That is the energy gap between two consecutive vibrational levels is 1/100th part of the energy gap between two consecutive electronic levels. Also, from the last equation, that the energy, that is from this equation in red, that also the energy gap between two consecutive rotational levels is 1/100th part of the energy gap between two consecutive vibrational levels. So we have obtained the expression for the energy difference between two consecutive electronic states, between two consecutive vibrational states, and between two consecutive rotational states. And we have also compared the magnitudes of these energy differences with respect to the energy difference in the between the two consecutive electronic states. So this completes the answer to the question. So this is the end of slide number 64.